For most of human history, we assumed the universe was stable or slowing down after the Big Bang. But observations changed everything. Scientists discovered that galaxies aren't just moving away from each other. They're accelerating as they do. It's as if something invisible is stretching space itself, pulling galaxies apart faster and faster over time. We call this mysterious force dark energy, but we still don't fully understand what it is or why it exists. The universe isn't just expanding, it's speeding up while doing so, and that changes everything we know about its future. Today we will talk about something is pulling galaxies apart. So before we start, make sure to hit the like button and subscribe to my channel. 1. The beginning of a cosmic surprise. For most of human history, the universe was imagined as eternal and unchanging, or at least evolving in ways governed only by gravity pulling matter inward. Even after Einstein introduced general relativity, many scientists still assumed the cosmos might be static or slowly evolving. That view changed dramatically in the 20th century when Edwin Hubble observed distant galaxies and discovered a surprising pattern. Nearly all galaxies appeared to be moving away from us. This was not because Earth was at a special location, but because space itself was expanding. The farther a galaxy was, the faster it seemed to recede. This relationship became known as Hubble's law, and it fundamentally reshaped our understanding of reality. Instead of being a fixed stage where objects move, space itself turned out to be dynamic, stretching and carrying galaxies along with it. But this was only the beginning of a deeper mystery that would emerge decades later. 2. The physics of redshift and expanding space. The evidence for an expanding universe comes primarily from the phenomenon of redshift. When light travels through space from distant galaxies, the expansion of the universe stretches its wavelength, shifting it toward the red end of the electromagnetic spectrum. By analyzing this shift, astronomers can determine how fast an object is moving away. In the mid to late 20th century, measurements of redshift became increasingly precise, allowing scientists to map the motion of galaxies across vast distances. However, the real shock came in the 1990s when two independent teams studying distant type Ia supernovae, used as standard candles for measuring cosmic distances, found something unexpected. These supernovae were dimmer than predicted, meaning they were farther away than they should have been if the universe's expansion was slowing down under gravity. Instead of decelerating, the universe was accelerating. This discovery overturned long-standing assumptions and revealed that something unknown was driving galaxies apart faster over time. 3. Dark energy and the hidden structure of the universe. To explain this accelerating expansion, scientists introduced the concept of dark energy. Unlike matter or radiation, dark energy does not clump into structures like stars or galaxies. Instead, it appears to be uniformly distributed throughout space, acting as a property of space itself. Observations suggest that dark energy makes up roughly 68% of the total energy content of the universe, with dark matter accounting for about 27% and ordinary matter only around 5%. This means that everything we see, planets, stars, galaxies, is only a tiny fraction of the cosmic budget. Dark energy is often associated with Einstein's cosmological constant, a term that represents energy inherent in empty space. In this interpretation, even a vacuum is not truly empty, but has a small, persistent energy density. As the universe expands, more space comes into existence, and with it, more dark energy, causing expansion to accelerate further. Despite its central role, dark energy has never been directly detected or explained at a fundamental level. 4. Gravity's limits and the battle for the universe. The expansion of the universe is governed by a balance between two opposing forces, gravity and dark energy. Gravity acts as an attractive force, pulling matter together to form stars, galaxies, and clusters. It dominates on small scales, which is why solar systems remain stable and galaxies do not immediately fly apart. However, gravity weakens over large distances and becomes less effective at counteracting the expansion of space. Dark energy, on the other hand, does not weaken with distance. Its effect becomes more significant as space itself grows. This creates a situation where, on cosmic scales, the repulsive effect of dark energy outweighs gravity. As a result, galaxies are not just moving apart. They are accelerating away from each other. Galaxy clusters remain bound, but everything beyond those structures is being pushed farther apart at an increasing rate, gradually reshaping the large-scale structure of the universe. 5. Einstein's cosmological constant and its revival. Albert Einstein originally introduced the cosmological constant into his field equations to counteract gravity and produce a static universe, which was the prevailing belief in his time. However, after Hubble's discovery of expansion, Einstein abandoned this idea and reportedly referred to it as his greatest blunder. Ironically, modern cosmology has revived the cosmological constant as the simplest explanation for dark energy. In this model, empty space has an intrinsic energy that does not dilute as the universe expands. This means that as the universe grows larger, the total amount of dark energy increases, amplifying the expansion effect. While this model fits observational data extremely well, especially measurements of the cosmic microwave background and distant supernovae, it raises deep theoretical problems. The predicted value of vacuum energy from quantum physics is enormously larger than what we observe, leading to what is known as the cosmological constant problem, one of the biggest unsolved issues in theoretical physics. 6. Alternative theories and scientific possibilities. Because dark energy is not fully understood, scientists have proposed several alternative explanations. One possibility is that dark energy is not constant but dynamic, represented by a field called quintessence, which changes over time and space. Another idea is that general relativity itself may need modification on extremely large scales, meaning gravity behaves differently across cosmic distances than it does locally. Some theories suggest extra spatial dimensions or hidden interactions between fundamental particles that could influence expansion. There are also hypotheses involving evolving vacuum states or phase transitions in the early universe that left behind residual effects driving acceleration. However, all these models must match precise observational data, including galaxy clustering, gravitational lensing, and the cosmic microwave background. So far, none have replaced the cosmological constant as the leading explanation, though research continues actively in this area. 7. The long-term fate of the expanding universe. If current observations remain correct, the universe will continue to expand at an accelerating rate indefinitely, over extremely long timescales. This will lead to profound consequences. Galaxies outside our local gravitational group will eventually move beyond the observable horizon, meaning their light will no longer reach us. As expansion continues, star formation will gradually decline as galaxies lose gas and existing stars burn out. Eventually, the universe may approach a state known as heat death, where energy becomes evenly distributed and no thermodynamic work can occur. In this scenario, the cosmos becomes cold, dark, and increasingly empty, with only isolated gravitationally bound systems remaining. Black holes may dominate the final stages of cosmic evolution, slowly evaporating over unimaginable timescales due to Hawking radiation. But if you like this video and would like to see more like it, please give it a thumbs up, leave a comment, and click the button to subscribe.